plan for today is to start talking about calorimetrics, which are basically Riemannian metrics with holonomy contained in the group U of M. These will include the holonomy groups U of M, SUM, and SPM, as these are all contained in UM or U of 2M. You have achieved coffee. Well done. Sorry? Oh, okay, right. You've stolen coffee. So we'll have a section 3.3 on calorimetrics. So, if we let X with complex structure J be a complex manifold, so then X is a real manifold, we can put Riemannian metrics on it. We can ask what are the best kind of Riemannian metrics on X. So if we've got a Riemann metric G, what compatibility conditions would we want to impose upon G and the complex structure J? Well, so firstly, we call G Hermitian if G of little u and little v is G of Ju and Jv for all vector fields U and V on our manifold X. So that means that J is an isometry. So J preserves the lengths of vectors using G. So that's just a pointwise condition. We're going to want to impose an extra condition, which will be a partial differential equation upon the metric G, in effect. So let's suppose G is Hermitian. And if G is Hermitian, we define the Hermitian form little omega. Okay, so before we do that, let's say in index notation, we have that G lower AB is equal to J lower A upper C, J lower B upper D, G lower C D. Okay, so if G is Hermitian, we define the Hermitian form omega of G by omega of U and V is G of Ju and V. So in index notation, omega is a tensor with two lower indices A and B, which let's say omega AC is a J lower A upper B, G lower B lower C. So it's a tensor of that type. Now let's look at vector fields U and V again. Little omega of U and V is G of JV and U, just by definition, which is G of U and JV, because G is a metric, so it's symmetric in its two indices. Now this is G of Ju and j squared v, because of the Hermitian condition. We can apply j to both sides and not change it. So this is now minus g of ju in v, because j squared is minus the identity, which is minus omega of u and v. So G is a metric, it's symmetric in its two indices. This shows that omega is antisymmetric in its two indices. Sorry, yes, exactly, yep, thank you. Omega of v comma u ends up being minus omega of u comma v. Okay, so omega is antisymmetric. So omega lower AB is minus omega BA, and omega is a two-form. And that only works because G is Hermitian. And in fact, it is a real brackets 1 comma 1 form. Well, you can think about real two forms as examples of complex two forms. You know, the complex two forms are the form alpha plus I beta, and then the real forms are the ones where beta equals 0. So as a complex two form, it's of type 1, 1. Because the complex two forms have splitting into 2 0 forms and 1 1 forms and 0 2 forms. So being a real 1 1 form means it lies in the intersection of the real forms and the 1 1 forms inside the complex two forms. Okay. So now we can impose an extra condition, which is that we call the metric G scalar. And we call omega the scalar form rather than just the Hermitian form if d of omega is 0. So the extra condition is that we want the two form omega to be closed. So that's a partial differential equation on the metric G and the complex structure J. Okay, so here's an important fact, a proposition. If we let X and J be a complex manifold, and G, a scalar metric, on X and J, with Levy-Civita connection nabla. So the conclusion is that nabla of omega is nabla of J is 0, and the holonomy group of G is contained in U of M, is contained in O of 2M, where M little m is the complex dimension of X, which is half the real dimension. Okay? So, well, let's have at least a sketch proof of this. Well, so since omega AB is J, well, let's say better, AC is J, A upper B, G, BC, And nabla of G is 0. By the definition of the Lebedev connection, we have that nabla D of omega AC is equal to brackets nabla D of J AB GBC. So ordinarily, when you differentiate a product, you use the product rule. So you get derivative of J times G plus J times derivative of G, but the derivative of G is 0. So that happens. And this operation with G that you're using G to lower an index, that's invertible. Well, basically, nabla of omega is kind of more or less the same thing as nabla of J, at least up to these invertible linear operations. And nabla of omega equals 0 if and only if nabla of J equals 0. Okay, so let's forget for the moment that J is a complex structure and G is a calorimetric. So if instead J is only almost complex and omega is not necessarily closed, then these derivatives, nabla omega and nabla J, well, this equation still holds, but these would not have to be 0. Then you can show that nabla omega, or more or less equivalently nabla J, splits into two components. And one of them is most obviously associated to omega, the other one most obviously associated to J. And so one is just, so one is d omega, which is really a chunk of nabla omega. So nabla d omega AC, because nabla is torsion free, d omega is what you get by anti-symmetrizing these three indices. So one is d omega, and the other is the Neuenhaus tensor, Nj of J, which is a component of the derivative of J, nabla J, with respect to any torsion-free connection, such as the Lebedev connection of G. Okay, so work to do to show that. But in our case, both of these components vanish. D omega equals 0 because it's scalar, and Nj is 0 because J is a complex structure, not an almost complex structure. So therefore, nabla omega is nabla J is 0. That hopefully justifies the first part of the proposition. And then for the Holonomy, claim about Holonomy groups, well, from section 2.2, tensors S with nabla of S equals 0 are in one-to-one correspondence with tensors S at your base point x0 for the Holonomy group on T x0 of x preserved, which are fixed by the Holonomy group of G, thought of as a subgroup of the automorphisms of the tangent space of X, and hence whole of G preserves, well, we know it preserves the metric G, well, it preserves basically a metric and a complex structure and the Hermitian form, or the Kähler form, at x0, or on, if you like, r to the 2m. So, and the group which preserves both the standard metric, the standard complex structure, and therefore the standard Hermitian form on r to the 2m is U of m, the unitary group in O of 2m. Okay, so that's all I'll say about that proof. Now, as a kind of converse to this proposition, if x and g is Riemannian, with the Holomby group of G is contained in U of m inside O of 2m, then, well, there is a complex structure J on X with nabla of J equals 0 and G is Kähler with respect to J. Of course, there might be more than one such complex structure. Well, for example, for any complex manifold, you can always replace J by minus J. Minus J will also be a complex structure, and G will be Kähler with respect to that. As we'll see probably on Monday, there's a class of things called hyperkähler metrics, where you have a whole family of complex structures with respect to which G is Kähler. Now, but if you're in some sense given a particular inclusion of Holomia group of G inside, so if you're given an inclusion of whole G inside a particular U of m, that defines a particular complex structure J, and so somehow this choice of inclusion, there might be several ways of including whole of G inside a U of m subgroup. Well, so really, I'm saying, well, whole of G is contained in aught of Tx0 of x, really. If you're given a particular inclusion of U of m into there, containing the image whole of G, then that defines a particular J. So in that sense, an inclusion of there and there gives you, makes G into Kähler in a kind of unique way. Okay, so well, so the proposition basically says, well, roughly says that d omega equals 0 implies, well, nabla omega equals 0, at least on a complex manifold when omega is the Hermitian form of a Hermitian metric. So this is basically a weak condition, where this is apparently a much stronger condition. And so, well, so this clearly implies that, because this is just more equations on omega than that. It includes some of those equations. And somehow this tension between the weak and the strong gives Kähler geometry some of its good properties. Okay, so the tension between the kind of weak condition versus a strong condition gives Kähler geometry some good behavior. At least morally speaking, it's not very precise, but basically, as d omega equals 0 is weak, it's easy to satisfy. And so you get lots of examples. Of Kähler metrics. As we'll see shortly, there are kind of huge numbers of examples of interesting manifolds which admit Kähler metrics, and any one of these things has an infinite dimensional family of Kähler metrics on them. So there's loads and loads of examples of Kähler metrics, but on the other hand, as nabla omega is 0 is strong, then Kähler metrics have very good properties. Okay, so usually, well, if you kind of impose a strong condition, you might get good behavior, but then you've ruled out lots of examples. If you impose a weak condition, you might get plenty of examples, but not very good behavior. But in this case, we manage to have both. We can have our cake and eat it. Okay, so let's talk a little bit about examples of Kähler metrics. So this is just a kind of first thing to get us going. Later on I'll talk about Kähler potentials and then about the Glaubig injector, and those will produce, well, will tell us more about just how many examples there are, really. Firstly, the Euclidean metric on c to the m, which is r to the 2m, if you like, is Kähler. And we might write it as G is mod of dz1 squared plus mod of dz2 squared plus dot 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 plus mod of dzm squared, where z1 up to zm are the complex coordinates on c to the m. So hence, if we divide this by some lattice in c to the m acting by translations, that will preserve the metric, so the metric will descend to let's say the torus t to the 2m, which is c to the m over let's say a lattice z to the m plus I times z to the m. This is Kähler. Or you could take a more general lattice downstairs if you wanted. That's a compact Kähler manifold. Another very important example is that, well, there is a natural u of m plus 1 invariant metric on CPM. So this is scalar. And it's called the Fubini study metric. Another way of, okay, well, so there's a, you can achieve this by thinking about the unit sphere inside C to the n plus 1 that has a natural projection down to CPM with fibre S1. On S to the 2n plus 1 there's the round metric given by restricting the Euclidean metric on here, and there's a way of inducing a metric on the base by the kind of Riemannian submersion thing. Basically you take the metric on here to be the metric up here, or the lift of the metric up here, restricted to the subspaces perpendicular to fibres, or something like that. That will determine for you a unique Riemannian metric downstairs on CPM, which is un plus 1 invariant. In fact, CPM is a symmetric space. Okay, so next, if we let X and J and G be a Kähler manifold, and Y, sitting inside X, a complex submanifold, meaning that Y is a real embedded submanifold of X, immersed, and the tangent bundle of Y is invariant under J as a subbundle of the tangent bundle of X restricted to Y. So then J restricts to a complex structure on Y. And then for H, which is G restricted to Y, is also a Kähler metric on Y. So that's because the Hermitian form of this metric on Y is a restriction to Y of the Hermitian form of X. And because the Hermitian form, the Kähler form of X, is closed, the restriction to Y is also closed. So, so part of this thing is that the Kähler condition has a linearity to it because it's d omega equals 0. The condition nabla omega equals 0 is not, in some sense, not really linear in omega, because nabla itself depends upon the metric G, which depends on omega. So that doesn't look like a linear equation in G, it looks non-linear, but this is a linear condition. And so then linear conditions behave nicely with respect to things like restricting submanifolds. Okay, so this is a Kähler metric on Y. If we use complex algebraic geometry, we can find lots and lots of complex submanifolds of complex projective spaces, CP, let's say CCB again, where usually you think about the ambient dimension big N as being large, and these complex submanifolds are called projective complex manifolds. So then, well, as CPN is Kähler by the Fubini study metric, all of these submanifolds are Kähler. So all projective complex manifolds are scalar. So every projective complex manifold has at least one scalar metric, which you get by restricting the Fubini study metric on CPN. But another thing that we'll see later on is that if a complex manifold has one scalar metric, then it's actually got lots. It'll have an infinite dimensional family of them, and you may be able to find metrics that you like better within that family than the restriction of the Fubini study metric, for instance, by prescribing their Ricci curvature. Okay, so let's move on to talk about the new section 3.4. We'll talk about the de Rham cohomology of scalar manifolds. Let's start off with X and G, just a compact and Riemannian manifold. So I want to remind you of some bits of the theory of Hodge theory for compact Riemannian manifolds, which is a way of expressing the de Rham cohomology in a slightly different way. And so let's write omega k of X for the the sections of lambda to the k t star of X is the vector space of k-forms on X. And so then you've got D goes from the k-forms on X into the k plus 1 forms on X is the de Rham differential. That's what we use to define the de Rham cohomology. Now, because we have a metric G on X, we can also form a map D star going from the k plus 1 forms on X back into the k forms on X. What's called the formal adjoint using the metric G. So this would have the property that somehow the defining property is that the L2 inner product between two forms d alpha and beta formed using G is equal to the L2 this is now for alpha a k form and beta k plus 1 form. So that's the defining property of this. So if that's all you knew about it, you might just think that D star is some linear map between k plus 1 forms and the k forms, but you might know what kind of form it was. In fact, D star is just a first order partial differential operator looking much like D does. You can give it a nice explicit expression for it in coordinates. It's local, it works on non-compact manifolds and smooth and so on. So that's D star. It's just some operator you can write down very explicitly. In fact, so D star is plus or minus star of D of star, where star is the Hodge star of G. Actually, you need an orientation to define a Hodge star, but because the Hodge star appears twice here, the dependence on the orientation actually goes away. So it still makes sense if G is not orientable. Okay, so, sorry? I think it's kind of formal because, well, because you're writing an equation like this. Not quite sure why that's called formal, but okay. So now let's write curly h to the k is the set, in fact, the vector space of alpha in omega k of x, such that d alpha is d star of alpha is 0. So forms alpha satisfying this are called harmonic. Well, okay, we're on compact manifold, so harmonic might also mean the kernel of d star plus d star d, but it's the same in this case. So this is a vector space of harmonic k forms. So then Hodge theory basically says that curly h to the k is naturally isomorphic to the kth de Rham cohomology group of x of the reals. Okay, so as a kind of sketch of why this Hodge theory is true, well, you have h to the k of x are, well, it's basically the kernel of d over the image of d, where that can be a dk, that's an image of dk minus 1, d on k minus 1 forms. So this is isomorphic to the kernel of dk intersected with the orthogonal subspace to the image of D, where this is the kind of L2 orthogonal. And then this is equal to the kernel of dk intersected with the kernel of dk minus 1. Well, no, this is really dk star now. Sorry, no, the star is there. And then finally, if you like, you can also say this is equal to the kernel of d star plus d star d. So, well, this is a bunch of operations on infinite dimensional vector spaces with the L2 norm. If you were doing them on finite dimensional vector spaces, these would be easy linear algebra. So this is saying that, well, quotienting by a vector space is kind of equivalent, is more or less isomorphic to projecting to the orthogonal complement of that vector space, and then this being that would be a consequence of the conformal property, adjoint property of this. Now, in the infinite dimensional vector spaces, none of these steps are quite obvious, because, well, it's not clear that the dividing by the image is the same as taking the orthogonal complement, but you have to do some analysis to prove all this works. Okay, so de Rham cohomology is isomorphic to this vector space of harmonic k forms, which satisfy d is d star is 0. Right, so now let's move on to Kähler manifolds. So now let x and j and g be a compact and Kähler manifold. So by the way, the reason we need a compact manifold is we're doing this kind of L2 integration, L2 integration by parts. And let's say if you're on a manifold with boundary, if you had a boundary, then the Stokes theorem would give you some extra term on the boundary, which you don't want. If you had a non-compact manifold, then these integrals might not converge, and so again that wouldn't make sense. Okay, so then, well, let's look at the real K-forms. We complexify them. These then become the direct sum over all p plus q equals k of the p comma q forms on X. So the vector space of K-forms is the direct sum of the vector space of p comma q forms. That's true on any complex manifold. And we can also split the de Rham differential Roman d as a partial d plus a partial d bar. And the formal adjoint d star of d also gets split as the formal adjoint curly d star plus the formal adjoint curly d bar star. Okay, so let's see if we can split this curly h to the k into pieces which correspond to PQ forms. Now, there's something special which happens with these operators, d bar, and their duals, their adjoints on Kähler manifolds, which is called the Kähler identities. So the Kähler identities are an equation that curly d star plus curly d star curly d. This is equal to curly d bar star plus curly d bar star curly d bar. And that's a half of Roman d star plus Roman d star Roman d. So these operators on a Kähler manifold just satisfy these. So this is true for Kähler metrics on a complex manifold, but it's actually false for general Hermitian metrics. So although these make sense for a Hermitian matrix, they're not necessarily true. Okay, now, okay, so it might be worth noting at this point that this is also equal to the kernel of d star plus d star d, because if you take the inner product of alpha and d star, or d star plus d star d alpha, that's 0, and then you integrate by parts. You get d alpha plus d star alpha, and those are the L2 norms of d alpha squared, L2 norms of d star alpha squared. So if you're in the kernel of this, then you also d star alpha and d alpha are also 0. So from the Kähler identities, we can deduce okay, so our vector space HK of initially real harmonic K-forms. Well, we want to work with complex forms, so let's complexify it. This is the set of alpha in the complex K-forms on X, with d alpha is d star of alpha is 0. This is the kernel of d star plus d star d, because of this L2 norm argument. Now this is now the kernel of d bar star plus d bar star d bar by the Kähler identities. because those two operators are the same up to the factor half. So this is now alpha in the k-forms, complex k-forms on X, for which d bar of alpha is d bar star of alpha is 0. And now the k-forms here are direct sum of pq forms. And if you think about it, for each pq component of alpha, these equations, these equations don't mix the different pq components of alpha, although these equations do. In this line, it's not clear that the kernel should be a direct sum of pieces of pq forms, because the d and d star equations here, they mix the different pq components. But for this one, the pq components are treated separately. So this is now direct sum over p plus q is k of the set of alphas in the pq forms on X, such that d bar alpha is d bar star of alpha is 0. Okay, and let's write this as the direct sum over p plus q is k of curly h p comma q. Curly h p comma q is a set of harmonic pq forms. It's just this set here. Okay, so but curly h p comma q is isomorphic to the straight h p q d bar of X, the Dolbeau cohomology. Basically by the same argument as in Hodge theory. So Hodge theory tells you that de Rham cohomology is isomorphic to curly HK. Same kind of argument here gives you this. So now we've got a conclusion, which is that the de Rham cohomology HK de Rham of X is isomorphic to the direct sum over all p plus q equals k of the Dolbeau cohomology hd bar p comma q of X, provided X is compact and scalar. Okay, so this equation would make sense for any complex manifold, but in general it's false if X is not a compact Kähler manifold. So if you like slightly more sophisticated mathematics, something that's going on is that there is a spectral sequence going from the Dolbeau cohomology to the complex de Rham cohomology, and for compact Kähler manifolds, this spectral sequence degenerates at the first page or E2 or wherever it is, which means that you can actually get a direct sum here rather than some more complicated relationship. Okay, so let's take a break there.